That takes us to a new topic, which is looking at measuring segments. And the starter for this is going to be kind of getting us into that idea here. And we're going to start off by doing some exploring. So we're going to draw a segment PD. I'm going to make it nice and big so I got plenty of room. And here we've got, if segment PD is 10 meters long, okay, I'm going to indicate that this is 10 meters. And I'm also going to say this is PD, and since it's the length, I don't use a bar above that. We've also got A is the midpoint, okay? So if A is the midpoint, I'm going to do some good notation stuff. I'm going to say those two are congruent. I'm also going to show that relationship symbolically. Segment PA is congruent to segment AD. And I'm going to show that numerically. So if this whole thing is 10, if this is the midpoint, the only way I can make those two equal is if each piece is 5. So we can say that PA would be 5 and that AD would be 5. And I'd like you to notice that I'm not using the congruent symbol there. I'm just saying those are lengths. I'm also not using the bar above those segments. That means we're talking about distances. Okay, so that's really part 2. So AD would be 5. All right, and then the third part, we've got B as the midpoint of AD. Okay, so I'm going to put another tick mark there. And if this is the midpoint of AD, what this means is that these two pieces are equal. So the way we show this, the first tick marks we made had a single bar, and here we're going to use double bars for each of these to show that we're talking about something different. So visibly, the way that I'd see this is with those tick marks, and then notationally this would be saying something like AB is congruent to BD. I could also say that AB is equal to BD, and if the whole thing is 5, that means the only way I can get there is if each of these is 5 cut in half, which doesn't come out clean. That's a decimal. I can call that either 2.5 on both sides or 5 over 2. Those mean the same thing. The big idea that we're getting at here is trying to make some sense of working with what we know so far in geometry about how these things are defined and stuff we know from algebra about solving some equations. We're going to be dealing with adding pieces up to make a whole, and we're going to be talking about what's going on as far as different types of lines and line segments. First thing we're talking about is something that's horizontal. Visually, we're talking about something that is going this way. This is a horizon. Anything that goes straight across right and left along the x-axis is going to be horizontal. And you might recall from Algebra 1 that if we're talking about something horizontal, the slope, which is defined as the change in y over the change in x, is going to be 0. So let's say the slope of this is 0. That does not mean no slope. That does not mean that it doesn't have a slope. It means that we're going up 0 for every one that we go over. Something that's vertical, that's what we call up and down, or anything that's like the y-axis. You might recall from Algebra 1, it has something we call an undefined slope. And the reason for that is that when we talk about the change in y over the change in x, this doesn't have a change in x. So if we're doing some number divided by 0, that's undefined. We cannot divide by 0. Looking at the difference between two numbers in a number line, so that's the next thing we're talking about here. You're asked to come up with an example, and the example that we might talk about is if we had 1, I don't know, and 7. Actually, let's go -1, 7. That's more fun. And thinking back to when you first started working with number lines, you may have started talking about, okay, I got to jump a certain number of things to get to 7. And then if I go from -1 to 0, and 0 to 1, 1 to 2, and 2 to 3, and 3 to 4, And 4 to 5, and 5 to 6, and 6 to 7, you might notice that that's 8 jumps. We then found ways to do this better, and by better, I only mean faster. So a faster way to do this would not be counting the jumps, but rather saying that the distance between these 2 points is really subtraction. 7 minus -1. We know if I'm minusing negative, that really means I'm adding it, is equal to 8. So then if we're talking about this more generally, if I have 2 points, and I'm going to call them, I'll make a vertical number line just to mess things up. Let's call this A and B, where A and B are both numbers. The length of AB would be equal to whatever B is minus A. And just to be a little bit careful with this, if you subtract them in the backwards order, we need to make sure that we make them positive by using absolute value. Absolute value is just going to talk about the actual distance between those two numbers, and that means we have a positive answer here. For about 99% of the things we do, you don't need to worry about that. All right. The next thing that we're taking a look at is to drawing segment AC. And here we've got AC, put B somewhere in between A and C, and then write an equation involving AB, AC, and BC. Okay, so if we've got AB, I'm going to do BC because that's kind of the other piece of that, and then we've got AC. And to me, it looks like if I take AB and I take BC, if I put those together, I get AC. So an equation for this might make sense if I did AB plus BC, and that's going to be equal to AC. And I guess that should have been on this side here, but that's okay. This has a formal name. This is called the segment addition postulate. A postulate is something that we accept as true, although we don't have something that's necessarily a good way to prove that. Or actually, it should be more specific. We don't have really any way to necessarily prove that. So looking at what we have going on here, we're saying that if you have a segment broken up into pieces, if you add those pieces together, it gives you the entire thing. We can do this with numbers too. Let's say that we want to look at a segment that was 7 and 3. If you want to find AC, we'd say 7 plus 3 is going to be 10. And we can do this with variables as well. If we instead had 5x plus 1 and 2x, and we're talking about the same 3 points, AC would be 5x plus 1 plus 2x, adding those two pieces together. That's going to come into play for what we look at next. We got a lot of words to talk about here. So we're trying to find the measure of Mn if M is between K and N. Okay, let's draw that out. So I'm going to break this down before I even try to look at the numbers here. So Mn, let's draw segment Mn. Mn and a segment. M is between K and N. Oh, come on. So M is between K and N. I'm going to make K over here. So now we've got Kn on the outside. M is between K and N. Okay, I'm up to that point. Km is equal to 4. Mn is equal to x. And Kn, I'm going to use a brace here to show this whole thing is equal to 25. And when I draw that, hopefully pretty easily I can see that these two pieces, the two segment parts, are going to make 25 together. And you might jump and say, oh man, I know that's got to be 21. But just for the sake of understanding what's going on here, let's call this 4 plus x is equal to 25. And by the way, we can do that because of the segment addition postulate. And if we do minus 4 to both sides, we get x is equal to 21. And what that means is that mn is equal to 21. All right, here we've got AB. I'm going to be a little bit careful here because I know that was a pain last time. This is going to be on some kind of a segment. And it says A is between B and T. So if we've got B and T, we've got A is between those. Oh, look, it's like bat. We've got AB is 2x, okay. We've got AT is 3x, okay. And BT is 35 centimeters. Same thing, I can see that these two pieces together make up this whole equation. So you might say to yourself, oh man, I know that this works if I have 5 pieces in total. Each one has to be 7. But again, we're going to make our equation. So we got 2x plus 3x is equal to 35. That means 5x is equal to 35. If we divide both sides by 5, we get x is equal to 7. All right, and that leads us to some things that we've already mentioned a little bit, but I want to be a little bit clearer as far as some definitions. The first is probably the most common word that we're going to use this year as far as relationships between things, and that's the word congruent. We use the symbol of an equals with a squiggle over it, I think it's called a tilde, to show something is congruent. And what congruent means that two things are identical. And when I say identical, I mean something specific. We're talking about the same size and the same shape. And one of the nice things there is that we can then use that language, and we're going to use this all throughout the year, but we can use that language to talk a little bit more about midpoint. We mentioned this briefly. So the midpoint is the point on a segment that we said breaks it into 2 equal pieces. And what would have been really helpful is if we had said 2 congruent pieces. And we did talk about that, and I said that those are slightly different things. But this is where we can go a little bit more in depth into that. So if we're talking about this in terms of this segment, if M is the midpoint, then we say that segment AM is congruent to segment MB. The big idea here is that congruent is talking about the 2 geometric things, the 2 segments themselves. It's saying that the 2 segments are identical. And again, we mark that with tick marks to show that those are congruent. If we had other things we're marking congruent, we might mark these with 2 tick marks each, or 3 tick marks each, or even 4 if we have a ton of stuff that we're trying to show are congruent on the same diagram. The other piece of this is that from this congruent statement we can also make an equality. The equality is about how long these pieces are. And we could say something like the length of AM, and just remember that the length is without the bar on top, is equal to the length of MB. Equals is about numbers. So anytime that we see an equal sign, we're talking about the numbers are equal. The length of AM and the length of MB are equal. Anytime we see congruence, we're talking about the shapes. So the shape of AM, both the size and the shape of it, and the shape of MB, both size and shape, are exactly the same. That's a congruence thing. All right, last piece here is the idea of a segment bisector. We already talked about the word bisector. Bisector means cut in half. A segment bisector is anything that cuts a segment in half such that it goes through the midpoint. Where we saw this before, we talked about a perpendicular bisector. A perpendicular bisector would have to be the same type of setup, but instead of going through at a random angle, perpendicular bisectors have to go through at a 90-degree angle. Segment bisector cuts this into two equal pieces. Therefore, if we say something is a segment bisector, we're really talking about something having a midpoint. Let's look at this in terms of a little bit of the algebra behind this. So we've got M is the midpoint of AB. Okay, I'm going to digest this before I even look at the numbers here. I'm going to try to draw this segment. So I've got segment AB. And it says M is the midpoint. That means a couple of things. And before I look at the numbers, I want to digest what's happening here. If M is the midpoint, I can say that AM is congruent to MB. And just to clarify why I'm saying that, I'm just going to say that M is the midpoint. It's always useful to kind of show your thinking of why you're making statements like this. And the idea here is just to make sure that you can follow your work later and that someone else can understand what you're thinking. So if we've got AM is equal to 6.5, we're trying to find BM. So BM is this length. If AM is congruent to MB, that means that these two have to be exactly the same. So if I've got AM, the length is going to be 6.5. That means that BM, that's the other half of this, has to be 6.5 as well. All right, so let's draw the second one. So we've got WR, and it's bisecting CP. I'm going to draw this a little bit backwards. I'm going to draw CP first, because that's what's being bisected. And then I've got WR doing the bisecting. And it's bisecting this at Z. So that means that the bisected one is cut in half. We don't know anything about WR, so I'm not going to put any points or labels on there. But I will say that CZ, the segment, is congruent to ZP, the segment. And I will say that this is because Z is the midpoint. And this time, we're not given a half of this, we're given CP, that whole thing. So that's kind of interesting. So the whole length of CP is 8. And if we're bisecting, we have two equal pieces. That means they've got to be 4 and 4. So I might say something like CZ, this is the length we're talking about now, is equal to 1/2 of CP, and that's just because it's been bisected. So I'm going to call this bisector. Just to, again, see that thinking. So if CP is 8, that means that CZ has to be 4. All right, let's move on. This is a nice big thing. Ooh, we got lots of pieces going on here. And we have a diagram given to us. So we're going to get to really have our first practice kind of marking stuff up. And we're going to start by trying to make sense of what's going on here. So we've got CX bisects AB. So I'm going to find AB, okay. And that means that AX and XB are equal. So let's mark that. AX is congruent to XB, and that's actually a little bit hard to mark because we have the other piece in the way there. That's annoying. Cool. Y bisects both CD and XB. So we have a point Y. We said it bisects CD. That means that CY is congruent to YD. It's really helpful to write down things as you kind of notice them, so if you have to use them later, you have access to those. Okay, so I'm also going to mark that on here as those two are congruent. It also bisects XB, so that's this part here, and that means that XY is congruent to YB. Nice. So I'm going to mark that with 2 tick marks on each of those. And that takes care of everything that we're given here. And just to kind of show where these are coming from, actually all 3 of these, we're talking about knowing that we have bisectors. And that's kind of the why we have these things. So now we've got AX is equal to 3. We've got CD, this whole thing, is equal to 12. Let's see what sense we can make of this. So if CD is 12, that means that it's cut into 2 equal pieces. Each half has got to be 6. And if AX is 3, based on that, I know that XB has to be 3 also. But 3 is cut into 2 equal pieces, so it's going to be 1.5 and 1.5. So let's go through this. We've got XB, that's this whole piece. That's going to be 3. Oh man, we've got centimeters and not centimeters. I'm going to call that centimeters also, just to make that clear. We've got AB, that's the whole thing, so that's 3 plus 1.5 plus 1.5, which is 6. CY is going to be just this top part here. We already said that was 6. And YB, that's just this piece here, is going to be 1.5 centimeters. What I'd like you to notice are a couple things. The first is that I really took the time to read the stuff that we were given, and from that, to mark up the diagram and to make some statements. I tried to be really clear about where these things were coming from, and then I applied the numbers. I figured out what I could figure out. I didn't even look at the parts I was trying to do until after I had already kind of marked up my diagram and made some statements about what we knew here. One of the things that we're going to get used to in geometry is the idea that we can make logical statements, and it's helpful to kind of organize our thinking beforehand because you don't feel lost if you do that. By doing all this stuff beforehand on this problem, we were able to get to the answers basically without having to do any of the work once we had to do A, B, C, and D. All that had been done while we were trying to analyze the problem.